Right, so welcome again to Unit 8, Mechanical Principles, and Assignment 2, and we're looking at Part 1 of Assignment 2. And on Thursday next week, we'll look at Part 2 for Assignment 2. So what we're going to look at today, we're going to, first of all, I'll talk about the assessment criteria for Assignment 1, Part 1. So we'll look at P4 and P5, which is the past components. So P4, what we're going to do is explain the effect of energy transfer in mechanical systems with uniform acceleration present. And that's covered in Activity 1, Tasks 1, and that's Part A, B, and C of Task 1. And then we'll move on to look at P5, which is to look at gyroscopic reaction torque. So we'll identify the magnitude of the effect of the gyroscopic reaction torque. But more importantly, we'll look at the effect of that gyroscopic torque. And that is quite difficult to try and get your head around, but we'll spend a bit of time on it, and hopefully at the end, you'll be able to follow what we're doing. Don't worry if you can't, it is quite difficult, and there's lots of videos online and they contradict each other. So, everybody has difficulty understanding gyroscopic effect. But anyway, we'll come to that in a minute. So in this presentation, we're going to start off with Task 1, and we'll do an example in preparation for you to do Task 1. And then for Task 2, what we'll do is look at the theory so that you're prepared to answer Task 2. Task 2 is relatively straightforward if you have an understanding of what's happening. So that's why we're not doing an example on that, because there's no point. It's better just to talk about the theory so that you get some understanding of this torque reaction. So I have a technical issue here. It doesn't want to change page. Just bear with us for a second. We can cut that out. That's it. It's working again now. So Task 1, we're going to determine the force to accelerate a mass upwards. And we're going to calculate the work done during that process. And then we're going to establish the change in potential energy and the change in kinetic energy, or the gain in kinetic energy would be more accurate. And we'll look at the addition of the potential energy and the kinetic energy and how that relates to the work done. And then in the second part, which addresses Task 2, we're going to discuss the vectors associated with a rotating mass that's subjected to a torque and comprehend, and I say the word comprehend, the concept of gyroscopic precession. Now that takes quite a bit of understanding, so please bear with us, and if we've got any questions at the end, we'll come back to that. Right, so first of all, let's take you back a little bit, and we'll look at Newton's second law. So when a body has an external force applied to it, it's going to accelerate in the direction of that applied force. And the acceleration is proportional to the magnitude of that applied external force. So what that says, it implies that the resultant force acting on this body gives rise to a change in the body's momentum. Now, momentum is the mass times the velocity. So the force, the applied force, is proportional to the change in momentum over a time period. That's also, to put that in an equation form, we have the mass times the final velocity minus the mass times the initial velocity. So that'd be the change in momentum, and that's going to occur in a period of time t. Now, if we separate that equation out, what we'll get is mass times velocity at the end minus the initial velocity, and that's going to be divided by t again. Now the change in velocity over time, that's known as acceleration. So we can say that the force is directly proportional to the mass times the acceleration. You've probably done this before, but anyway, we'll do it again. Now what we're going to do, we're going to use the SI units, and we can say that one force can be defined as the force required to give a mass of 1 kilogram and acceleration a of 1 meter per second. So what we had as a proportionality now becomes an equals. So the force is equal to mass times acceleration. So F equals ma. And I'm sure you're familiar with that expression. Moving forward, we'll discuss potential and kinetic energy. So first of all, potential energy, and there's three sort of common types of potential energy. So the energy possessed by a body due to its position or state, that's the formal definition of potential energy. So types of potential energy, and the one we're probably more familiar with, is energy due to a height above a datum. So that's gravitational. So that potential energy is defined by mass times g times the height above the datum point. We also have energy due to compression of a spring. So that's strain energy, so that stores energy. And also we can have energy due to compression of a fluid, more likely air. So we put compressed air in the cylinder, and we can use that compressed air to drive air tools, and so forth. So that's energy storage. That has potential energy to do work. We'll also look at kinetic energy. So the kinetic energy, and I'll just read it as out, the energy possessed by a body because of its motion. So if it's not moving, it has no kinetic energy. And it's equal to 1/2 of the mass of the body times the square of its velocity. So you're all probably familiar with this equation, where the kinetic energy is equal to 1/2 mv squared. All right, so we've looked at Newton's law, and we looked at the definition of potential energy and kinetic energy. So what we'll do, we're going to apply those laws to a relatively straightforward question. So we've got a mass of 50 kilograms, and it's accelerated vertically upwards off the floor by a crane through a height of 8 meters in 4 seconds. Excuse me. So the work done, we need to calculate the work done in raising the mass to this height. We'll also look at the gain in potential energy, and we'll also look at the gain in kinetic energy. And the reason for doing this, we need to see the relationship between the gain in potential energy and the gain in kinetic energy and the work done. So always start these questions with a free body diagram. So we're drawing a free body diagram. We have gravity acts on it, which acts downwards to a value of mg. And there's a tension in the wire pulling the mass upwards, and it's being accelerated upwards in that direction. So the net force causing the acceleration, net force F net, is the mass times the acceleration. But the net force, we have to look at the net force, is the difference between the tension in the wire less the force acting down mg. So the net force is T, the tension in the wire, minus mg, which is acting in the opposite direction. So therefore we can write down that T minus mg is equal to the mass times the acceleration. Okay, we'll go over to the next sheet. Right, in answering these questions, and you should do this with all questions that you attempt to do where there's some numerical analysis to do. The first thing to do is to look at the equations that are applicable. So this time we're looking at linear motion. So write down the equations of linear motion. We know we've got an acceleration. So the first thing we can do, see the top equation, what we can do, that only applies to a constant velocity where there's no acceleration. So we can actually just draw a line straight through that. We're not going to use that equation at all. So just draw a line through that. Right. we'd write down the information then we have from the question. So you can see all the numbers there. We've got displacement s, time t. We haven't got the velocity, the final velocity. I've put that in red for the time being. You'll see why. We need to determine that. We've got the initial velocity and we've got the acceleration. So the first thing you should always do is take what information you have from the question and see what you have, how that relates to the actual equations. So we've got our value of s. So the best thing to do is always tick them off. So we've got s there. So we've got that information. We've got s in that one, and we've got s in that equation. Okay, so I don't think it's anywhere else. So it's a good process to go through to answer questions like this. The next one is the time t, which is 4 seconds. So we have that. So we have the time t. So we have that time there. We have time there. And we have time in that equation. And we have time in that equation. Okay, so we move on to the next information that we have. We know the initial velocity is 0 because it was on the ground. So we know that the initial velocity, we have tick. We have the initial velocity in that equation. We have the initial velocity in that equation. And we have the initial velocity in that equation. Now, we weren't given the acceleration or the final velocity. So that's all the information we've got now. So what you need to do is you look at these equations then and say, which ones can I actually do some analysis on? Which ones can I determine the unknown quantity? Well, the first equation, there are 2 unknown quantities. So forget that, can't do anything with that one. The second one, we know all the properties apart from the final velocity. So we can use that equation. So let's see, we'll tick that off. We'll just change the color. So we can use this equation. We'll put a tick there. We can use that equation. The next equation, well, we haven't got the acceleration, so we can't use that. And the bottom equation, we can't use that at the moment. But we can use this equation that we've got highlighted here. So what we're going to do, we're going to find the final velocity v. So we'll use that equation that we've just identified where we can solve v. And we have s is equal to u plus v over 2 times the time t. And what we'll do, we'll rearrange that to give the velocity in terms of the other variables. So the velocity is 2s over t minus u. Now, if you're uncomfortable with this transposition of equations, put the numbers in the initial state and then work out what you don't know and then transpose the equation. So finally, we can calculate the velocity. We have the distance s, we have the time 4 seconds, and the initial velocity was 0. So we've got the final velocity of 4 meters per second. Now we can put that back into our properties, and these are usually the 5 properties that we need that accompany linear motion. So we've got the final velocity, and we can put that in, that's in red. So I've already done that. So now what we can do is we can go back to our equations and say, right, we've got the final velocity. So we can tick that equation there. We can tick v in that equation, and we can tick v in that equation. We could have used this equation here, by the way, to find the acceleration. But what I've done, and there's different ways of doing it, so there's no prescribed way of doing it. You can do whichever way suits yourself. So next thing we're going to find is the acceleration, because the only value that we haven't got. So find the acceleration a. Now we can use a whole host of equations here now. So we'll put them in a different color again. I've lost my mouse somewhere. Where's it gone? It's a bit small on the screen, so I need to change the color. So we'll go for blue this time. So which equations can we use now? Well, we can use that equations to get the acceleration. We could have used this equation as it was to get the acceleration, And now we can use this equation. It doesn't matter which one you use. They're all going to give the same answer of the acceleration that we're missing. So what we'll do is I've used the bottom one only because it looked a little bit easier. Maybe the top one is a bit simpler, but anyway, that's the one I've used. It doesn't matter. And rearrange that to get in terms of the unknown variable A, in terms of v squared minus u squared over 2s. And if we calculate that, put the numbers in, we'll get a final acceleration of 1 meter per second. So that's our 1 meter per second. And we'll put that back into our acceleration. So we've got all 5 properties now that define that motion. So now we can come to solving the question. So find the tension in the crane wire. We know from the previous page that the tension is equal to the tension minus mg is equal to the mass times the acceleration. We now have, always had m, we have g, we had m from that side, and now we've got the acceleration. So rearranging that equation, we can get the tension is equal to mass times acceleration plus this time mg. So if we put the numbers in, we find that the tension in the wire has to be 540.5 newtons. So I'm just going to go back and change my pen before we go to the next page. Back to red so I can see it better. So we'll go over onto the next page. And now we're really answering the question. So the work done is simply the applied force times the distance moved. So the applied force was 540.5 times the 8 meters, and that gives us 4,324 joules of energy required to lift that weight. Now what I want to do is look at the gain in potential energy. So remember, potential energy is due to its position above the datum. The potential energy is given by mgh. So if we put our values in of mass, g, and height, which is 8 meters, then that gives us 3,924 joules. And we also need to look at the gain in kinetic energy because it's accelerated upwards, so it's gained velocity. So we're looking at the velocity at the end, so that's the kinetic energy that it's gained. So the kinetic energy is half mv squared. We put the values of m and v into there, and that gives us 400 joules. Now, what I want you to do, if you add the gain in potential energy and the gain in kinetic energy, we add the two together that we've done there on that page, we find it's equal to 4,324 joules. And amazingly, it's the same as the work done, and that's it should be. So you've done that much work, that energy can't disappear, so it must equal the gain in potential energy and the gain in kinetic energy. Of course, we ignored things like wind resistance that might occur, but that's relatively small anyway. So hopefully that will help you quite a bit with task 1 in activity 1. So now we're going to move over to the next one, which is the gyroscopic effect. Now, this is a little bit more fiddly, so we'll try and take our time on it. And it does require you to think what you're doing as you go through the process. So imagine we've got a mass here, circle, and it's moving in the vertical direction with a momentum p. So it's mass times its velocity. And then it's acted upon by a force. So the example I've seen, it could be a hook on an ice, and it's going straight up in that vertical direction, and somebody clobbers it with an ice hockey stick, and it moves with a force in that direction, the horizontal direction to the right. What will happen, and you can envisage this, what will happen is that the momentum will move in the direction of the force. So you'll get what we call a new momentum, which will be in a different direction, and I've called that P with a dash. The point to note on this slide is that the momentum will always follow the force. So you can see the force goes off in that direction, and the momentum follows that force. Now that's very important to remember that fact when we're looking at rotational motion. By the way, the images are from Physicist, and there's a link there. It's an excellent video. So if you get a moment, have a look at that video. It really explains gyroscopic effect in some good detail. Right, now and this slide, this image is taken from the same source as well, but I've added a few extra bits to it. What we need to do now is to determine the rotational momentum vector. So spinning disks have an angular momentum, and we're going to give that symbol L. Now, to find out the direction of that vector, what you have to do something called the right-hand rule. So use your right hand and you wrap your fingers around the direction of rotation. So you can see there, it's rotating, looking from the front, it's rotating anti-clockwise, taking this as the front, it's rotating anti-clockwise. So we're using your right hand and the thumb points in this direction. So you can see that the direction of the angular momentum is indicated by your thumb. Yeah, so hope that's relatively clear. So think about that again. Wrap your fingers around the axis of rotation, and the direction of your fingers must follow the rotational direction, which is wrapped around the axis, and the thumb will point in the direction of the momentum vector. Now we've got to think of another force that can act on our spinning mass. So again, we're going to use the right hand rule. Now what we have, this is the shaft going through our spinning mass, still spinning in the same direction. And what we're going to do, we're going to apply a force upwards at this end. So apply a force upwards here, and apply a force downwards there. So what that does, because that's at a distance from the actual mass, it's going to produce a torque around this axis. So it's going to try and turn it in the vertical plane. Yeah. Now, what we need to establish is the torque vector. Again, we use the right-hand rule. So we look at the direction of these forces and the torque that it applies, and we see that it's actually trying to turn that whole mass disk. It's trying to turn it in this direction that's shown here. Yeah, so again, we wrap our fingers around the direction of the torque is trying to turn that mass. And like before, our thumb points towards what we call the torque vector. And we're giving that the symbol tor in there. Right, so that's very important to get that right. If you don't get this bit right, then the rest of it sort of won't work at all. So you've got to think about the direction that the forces are applying a torque onto that mass. Wrap your fingers around the direction that torque's applying, and your thumb will point in the direction of the torque vector. Now what we're going to do, we're going to combine these two images, this image and the one from the previous slide. So what we have the momentum vector, L, which is acting along the axis in this direction due to the way that the mass is rotating. And we have a torque vector due to the torque applied by those external forces. And what will happen, and this takes us back to the original linear motion, the momentum vector tries to follow the torque vector, or the force equivalent of the force. So what will happen is this will rotate in, the axes will rotate in this direction, in that plane. Now, if we just go back a slide, instinctively, you would have thought if I apply that force there and this force acting down at the other end, that it would rotate around that axis. Similarly, it would rotate around this axis. And this side would go up and this side would be going down. However, that's not the case with gyroscopic effect. What happens is the momentum vector proceeds towards the torque vector. So it's not intuitive. It's not what you expect to happen. And that's the problem with it. With looking at gyroscopic effect, it's not intuitive. Yeah, so now that we've understood the basic principles, I'm going to apply it to a couple of examples, and hopefully that'll drive home the message. So look at this aeroplane. We have an aeroplane here. It has an engine and a propeller, so there's a rotating mass. And looking at the front, it's a counterclockwise direction. From the back, it's clockwise. And we're going to look at it as if it does a left-hand turn. So looking from the top, it's going to turn towards the left. Yep. That's away from us, the front going away from us, from the picture. So using the images before, the disc here represents the propeller and the engine inertia. And the blue line is the axis of the propeller and the engine. So first of all, we've got to find the momentum vector. So again, we look at the direction. So the direction is counterclockwise or anti-clockwise. So we wrap our fingers around the axis in an anti-clockwise direction, and the momentum vector will be in the direction given by your thumb. So that shows the momentum vector acting in that direction. Yeah. Likewise, you've got to look, it's turning to the left. So that could be you turn the rudder and it will turn the aeroplane to the left. So what will happen, we need to look at the torque. So if we look at our inertia wheel again, which represents the engine and the propeller, to cause it to turn, you'll have a force, a horizontal force in that direction at the front and a horizontal force in the opposite direction at the back. This is all caused by the rudder, of course. So that has a torque trying to turn this in this sort of direction. So you can see using the right hand hand rule again, to get it to turn to the left, the torque acts in this circular direction. So this is the direction of our torque. So it acts in that direction. So again, we wrap our fingers around in the same direction as the torque being applied to the system. And we'll see our thumb is this time pointing upwards. So the torque vector is in the vertical direction. So this time we've got the torque in the vertical direction. And again, what will happen is that this will move towards the torque. So the momentum vector is going to move towards the torque vector. It's going to move in that direction, in that plane, which it does do if you look at the last slide. What the net result of that is that the front of the aeroplane will go up and the back of the aeroplane will go down. So the nose will lift and the tail will drop, as shown in that image at the top. So that's as a result of applying a torque through the rudder. Now we're going to look at another one, very similar, but this time we're going to turn to the right. Again, the same process again. So we've got the same engine going in the same direction, clockwise, counterclockwise, looking from the front. So our momentum vector is going to be in the same direction. However, the torque vector is in the opposite direction because it's trying, if you look at the direction of the forces causing the torque, then they're trying to turn it in the opposite direction. So again, we wrap our fingers around the direction that the torque forces are trying to achieve. And we look, our thumb is pointing down this time. So the torque vector is down. So we come back to our expressions. We have our momentum vector and our torque vector. And what will happen is this torque vector, the momentum vector is going to try and turn towards the torque. That line's gone. And that's exactly what happens. So if we translate that to the airplane motion, the nose will lift and the tail will drop. Actually, that's not right, is it? So let me do that correction before we do any further. So there's a correction there. Oh, I've lost it all. Let's just get it back. In fact, I'll change that right now. So the nose will drop and the tail will lift. I'll make sure I'm still sharing the screen. Still sharing, okay. Okay, so sorry about that, made a correction, and I've read that many times and I never noticed that error. So we'll just come back now to the last slide, last example, which is an example that's in the workbook. So again, to get the torque value, the gyroscopic torque, that's given by the moment of inertia times omega x, which is in the direction of the momentum vector, and omega y is the rate of the radians per second of the turning motion of the actual vessel. So what we want to do, again, we're going to represent the turbine in this ship by our disk. And what we have to look at the momentum vector and the torque vector. So first of all, the momentum vector is given to us, but again, you can apply the right-hand rule to that to find that the momentum vector is in the direction that the ship's actually moving. So the only other thing that we need is the torque vector. And because it's turning to the right, then the torque vector is as shown, where you wrap your fingers around the direction of the applied torque or the applied forces to give the torque vector, which is going to be in a downward direction. So if we look at our direction, what will happen is that the momentum vector is going to be forced towards the torque vector. So the result is that the bow of the ship will go down and the stern will go up. And that's very similar to the example that's in the book. So this should help you with task 2. I hope you've understood that. If not, please feel free to get in touch and we can go over this again. But I think that should be enough to help you with answering task 2 and activity 2. So just a note to finish on your assignment. You need to include a contents page. Identify each task either by the letter or the number, so we know which question that you're answering. Type up all written text. So equations can be handwritten and scanned, but they have to be neat. Yeah, otherwise we might not be able to read them. And we might not be able to mark it for you and give the appropriate mark. Use images, tables, charts, etc. to support your answers. Now, don't forget, you must always refer to these images, tables, charts, etc. in the supporting text. So for example, if you write something, you should really link it to the image by saying things like, as shown in figure 2. Otherwise, the figure has no value. If you don't talk about it in the text, then it has no value putting it in your report or in your coursework. So the last thing, include accurate citations and referencing. Referencing lists needs to go right to the very end, and the citation, all that means is where in your work have you used those particular references. So are there any questions? So we'll just move on to the last slide, which gives you my contact details. And then we're going to stop recording and see if there are any questions. Okay, so we'll stop recording now. Thank you.